Hey everyone, welcome to this explainer. So today we're unpacking an absolutely massive paradigm shift in modern cyber exfiltration using a really groundbreaking framework called CloudBurst. Now, if you've ever wondered how on earth security teams track down attackers when the digital crime scene, practically evaporates into thin air, well, you're in exactly the right place. We're going to look at the ultimate guide to understanding how we actually catch the people stealing our most sensitive cloud data. Let's get right into it.
Okay, let's dive right into our investigation blueprint. We've got 5 parts today. 1. The vanishing crime scene. 2. 6 cloud beacon vectors. 3. Scoring cloud attribution. 4. The 48-hour ticking clock. And finally, 5. Building better cloud traps.
Starting off with Part 1, the vanishing crime scene.
So think of post-exfiltration attribution, basically figuring out exactly who stole your data after a breach, as a high-stakes digital detective story. But here's the central mystery we're dealing with. How do you track an attacker when the crime scene literally vanishes, right? In traditional, old-school setups, you just trace an IP address back to a static server. Easy. But in modern cloud-native environments, we have to deal with this incredibly frustrating thing called infrastructure ephemerality. Because of stuff like Kubernetes pod autoscaling, the actual container or machine that fired a tracking beacon often doesn't even exist anymore by the time your investigation begins. The digital footprints are just gone. Poof.
And that brings us to a really crucial point. Our old threat models are dangerously outdated at this point. The old myth was that attackers were simply breaking in to steal static documents from file servers. But today, the reality is entirely different. Attackers are stealing S3 presigned URLs. They're compromising container images, lifting Kubernetes secrets, exploiting Terraform state modules, and hijacking IAM role tokens. They aren't just stealing a file anymore. They are literally stealing the keys to your entire cloud data estate. It's a whole different ballgame.
Which leads us perfectly into Part 2, 6 cloud beacon vectors.
Look, if the attackers have completely changed up their methods to steal cloud infrastructure credentials, we've got to change our tools, right? We need new types of digital traps, basically cloud-native fingerprints, that we can strategically scatter across our environments to catch them red-handed. And this is where the CloudBurst framework comes in. It introduces 6 specific passive beacon vectors that you can deploy across all the major cloud providers: AWS, GCP, Azure, OCI, the whole shebang. We've got S3 presigned URLs, watermarked container images, Canary IAM roles, poisoned Terraform modules, Kubernetes secret beacons, and serverless function triggers. Each one of these represents a unique trap totally tailored to exactly what modern attackers are trying to exploit. Now, when we evaluate and profile these different traps against each other, some fascinating patterns emerge. For instance, if you look at the profile for Canary IAM roles, it's highly balanced and really safe. It's incredibly robust against that disappearing evidence problem we just talked about. But then contrast that with the profile for Kubernetes secrets. That one is highly volatile. It carries a massive ephemeral risk simply because those pods restart and cycle out so incredibly fast.
All right, moving right along to Part 3, scoring cloud attribution.
Okay, so obviously it's not enough to just blindly scatter these traps everywhere. We need a structured mathematical way to actually score the quality of the breadcrumbs an attacker leaves behind when they trip one of these alarms. Basically, we need to know, is this evidence actually good enough to pinpoint the culprit? That is exactly where the Cloud Attribution Score, or CAS, comes into play. Now, don't worry, you don't need to memorize the raw math here. Just focus on these 4 core components. First, callback fidelity, which measures how good the info is before it gets scrambled by a VPN or Tor. Then we have IAM coverage, and the multi-cloud bonus if we happen to catch them crossing different cloud platforms. But the absolute crucial one to watch is the ephemeral penalty. We actively penalize the score based on how fast the cloud erases evidence due to routine infrastructure churn.
Let's jump into Part 4, the 48-hour ticking clock. And here it is. This is the absolute climax of the framework's findings. 48 hours. That's it. That is the uncompromising ticking clock you have before attribution data virtually disappears entirely. Think about that. If you're defending a network, why this matters is starkly simple. Your traps absolutely must trigger, and you must collect that telemetry immediately or it becomes completely useless. Let's break down exactly what happens during those 48 hours. When you deploy a beacon, your cloud attribution score starts off really strong, sitting pretty at about 0.79. But then, there's this terrifying cliff. Within just 48 hours, as containers naturally restart and your typical auto-scaling events happen, that score absolutely plummets to near 0.18 across all vector types.
It's crazy. The evidence is simply overwritten. The environment practically eats its own footprints.
Let's bring it all together in Part 5, Building Better Cloud Traps.
So, the big question, how do we actually fight back against an environment that destroys our own evidence? Well, now that we understand the brutal reality of this ephemeral decay, let's look at the practical takeaways for deploying these beacons out in the real world. If you're a cloud architect, pay close attention, because here is what you should take away from this explainer. We have two standout traps. The best overall, that's the Canary IAM role. It rocks the highest CAS score at 0.450 and has the lowest ephemeral risk because CloudTrail logs are persistent. I mean, even if a pod dies, the log remains safely stored. On the flip side, we have the most stealthy option, S3 presigned URLs. These boast the highest detection resistance at 0.890 because their normal-looking structure brilliantly evades modern cloud-native security scanners. It's a real game changer.
But the data also reveals a really hard truth about cloud defense. When we plot out the ideal zone for high-confidence attribution, basically that top-tier perfect evidence zone, it's completely empty. No dots at all. And this brilliantly illustrates an incredibly important honest null result from the research. It tells us that no single trap, regardless of how perfectly you configure it, reaches that high-confidence threshold on its own against advanced attackers. There's no magic bullet.
So, what do? We build a layered deployment strategy. Because no single trap works perfectly alone, we break it down into tiers. Tier 1 is universal. Deploy your persistent anchors, those IAM canaries and S3 presigned URLs first. Why? Because they survive the infrastructure churn. Then, Tier 2 is caching aware. Deploy your poison Terraform and container images next. And finally, Tier 3. You add in your high-risk, runtime monitored traps, like Kubernetes secrets, last. The absolute crucial takeaway here is that those Tier 1 persistent anchors absolutely must be present to maintain the trail when everything else simply evaporates.
Which leaves us with a totally fascinating and honestly pretty provocative challenge. If even the best, most mathematically optimized cloud traps leave a small gap in attribution, what behavioral signals are we going to need to finally catch the ultimate advanced persistent threats? The researchers suggest that adding supplementary signals, stuff like mapping out cloud infrastructure graphs or analyzing the temporal clustering of attacks, might just be the final key to closing that ultimate attribution gap. It's like a giant puzzle. Definitely something to think about as you review your own cloud security posture. Anyway, thank you so much for joining me on this explainer. Keep your eyes open and keep learning.